Hello everyone. So welcome to the Lab-03 of Design Compiler. In the last session, we saw how to set the design constraints, how to set the environment constraints, and compile the design. We saw how to create a clock. So I have just loaded all the commands that I set here. So you can type a command called history. So this is what I did. I'll just review these steps once more. We set the search path. We set the link library, target library. We define the design layer. This is we read in the all the RTL files. We elaborate. Now at this point you should check the warning on the web. After elaboration, you should check the inference report. What all clocks are inferred. How the case logic is inferred, whether it's full case or parallel case. When we start setting the environment conditions, which is set operating conditions, I'll discuss about this command later. So set operating conditions. I forgot to set Y load. We could do that. Let's assume whatever default Y load it is, let it take that. It will not be a problem. We set the input transition on input ports. We set the load. I also discussed how to estimate the value of input transition and load by looking at the library. Then we go on and set the design constraints. We set the clock. We set the uncertainty, the clock transition. Then we set the input delay and the output delay. So here in this case, the max delay and the input delay is set for both max and min cases. We will see the usefulness of this when we come to the static time analysis in minute 5. So this is you could also define variables in DC. It's a tickle interface, so everything that works in tickle works here. So you could define the variables like this. So input ports, we define variable input ports. Remove from collection all inputs, and we remove the clock port. So we define the input delays and output delays using these variables. And now I go ahead and compile. So last session we saw that compile ultra by default will ungroup some blocks. It will ungroup some hierarchy. And to start with, we do not want that. Obviously, it results into a load area, but in many cases we do not want that. So how do we do that? I just search for a variable that affects this by looking at the ungroup. Let me see. Yeah, so what we would do is we would run compile ultra in a simple format by using no auto ungroup, no boundary optimization, and no sequential algorithm. So in the next few lecture sessions, we will see in detail what each of these means and how does each of these affect synthesis. So meanwhile, let us remember that when you want to do a simple synthesis without scan, without any sophisticated optimization technique, this is the command you should use: compile ultra minus no sequential output inversion, minus no auto ungroup, and minus no boundary optimization. So this is the you could use no design rule and only design rule to control, or incremental to do multipass synthesis. Multipass means you want to do synthesis in 2 or 3 iterations. But for one pass synthesis, this is the basic command. So we will do that, and so it will start running synthesis. Now, after the synthesis is done, what we would do is we would learn about the report commands. That means now the synthesis is done. You want to check for all sort of issues. You want to verify that the netlist you have generated, the area and the timing results are fine, whether they are in line with your goals or not. What if some of the design rule is violated? How do you? And we will see what all reporting commands we could use, what all reporting commands DC provides us for reporting and analyzing issues. Right? So it's going through synthesis. It goes through different sorts of phases: sequential optimization, delay optimization, design rule fixing. Then it will go into the area recovery phase. So it's a good thing that you should at least once look at this compile log to see that sometimes what happens for few blocks, it will take a long time in one of these steps, either delay optimization or area recovery. Then you know that something maybe is not right with your constraints, it's taking too much time. Few of the blocks I work on take more than a day in some of the cases. So I usually try and make sure that my constraints are all right and try to decrease the runtime, because we do not want big runtimes for blocks, because each error, then each resolution of an error will mean that much time added to your to the block. So it's difficult to get that block out in time for the backend. So it's very good practice to review this compile log to see how much time it is taking once per block, right? When you start synthesizing a block. Now I'll write out the netlist minus format verilog minus output. I'll write in chip.p or overwrite this file, and I want to write the complete hierarchy, just single popular model. So now let's see. Let's once look at this netlist. So now let's look at the modules. So we see that now we have all the modules here. So they can ungroup, and right at the end you would have the top level module chip top. And you notice that since the RTL was more or less structured, there were very few. There was not a lot of glue logic. So the only glue logic that is synthesized is the 4 inverter and an OR gate. And all these modules are instantiated here. You could go to one module and see. This is the module. It only has a couple of memory instances. For example, the module above this. So memory X hierarchy, memory Y hierarchy, this memory. So this module power controller has a lot of standard cell logic. It has a lot of flops. So these DFS are nothing but they are flops. So all the flops here would be non-scan flops. They will not have a test TI pin. They will simply have a B pin. Why? Because we did not do a minus scan. We'll also see what happens when we do a scan option. We'll do that later. So this is the netlist. Now let's go back to design compiler and learn about the various reporting commands that are provided for us. So first I would discuss there's a simple command called report design. So you could know about all the report commands by doing report start or report underscore start. So these are all the report commands that are available to you. Many of these commands are restricted for specific use cases. There are various features of design compiler, like design compiler graphical, design compiler topographical. So some of the commands will work only there. So we look at one of the more famous commands. We've already looked at few. We have looked at report lib. We've looked at report clock. So okay. So first thing, let's get a design summary by doing a report design. Let's see what the options are. So report design just has no split and a physical option. Physical is not applicable for us. It is applicable for DC topographical, where flow time information is also provided, but we will not be looking into that. The no split is a option that is common to a lot of report commands, and it means that whenever the line overflows, it will not split the line. So whenever you are viewing it on screen, then it's all right not to give this option. But whenever you are writing into a report file, I would recommend giving the no split option. So right now I'm viewing it on a screen, so I'll just do report design. So now it gives me a summary of environment. It gives me a summary of libraries view. It gives me what is the link library. It gives me if I have provided any restrictions on the type of flip flops and attributes I haven't. So there's one specified. It tells me what is the operating condition here. It tells me what is the Y load model. Now in this case, I did not apply a Y load model for this session. Last session I discussed about the command that you can use to provide a violate model, but this particular version of standard cell library contains the automatic violate selection. So it is selected automatically from the total cell area. The default is a top, so it will apply only, it will take only the top level violate model for all the hierarchical designs. Okay, so it is not using top, it is using close. Okay, fine. And it gives us it is strange why it is not giving input delays and output delays. Let me just check the report port command. So report port can be used to check what all. So input delay is there, and so there may be a problem with the report design parameters. So sometimes there are bugs in the tool version. So here it tells me that there are in fact input delays specified. So what about the output delay? Yeah, output delay is also specified, but strange that report design does not tell us that. It tells us that input delays are not specified, output delays are not specified. It says that there are pin input delays and pin output delays, but what we have specified as port, we have specified input delays and output delays are usually specified at ports. There are some cases where we might want to provide input delays and output delays for some internal pin, but that is not recommended. It is used for very special case which is outside the scope of this course. So don't worry about it. So yeah, report design will tell you what all. It just gives you a summary of all the design parameters. So I would recommend to use the specific cases. For example, if you report the specific commands, for example, you could do a report lib for library. You could use a report violate model to check what violate model is used. So this is the report violate, which is much more. It provides much more detail than report design. So looking at the report design, I would recommend use the more specific reporting commands. For example, you could use report port minus verbose to check that whether the input and output delays you have applied are in fact there, in fact being read in by DC. Again, we saw this report block. We can verify what clock is specified here, what is the frequency of the clock, what is the waveform DC is using. Then there's a very interesting command called report QR, which reports a summary of the quality of results. Let's see that. Let's see whether it gives any option. So let's see the summary first. So significant digits will be used for timing numbers, timing and violation numbers, where you could say that I guess by default it's 2 or 3. I guess I think it's 2. Yeah. The period is being reported as 2.00. So the by default the significant digit is 2. I guess. Let's look at the summary first. So now it tells us that it gives us the timing summary. So it tells us that the worst negative slack is 2.99 nanoseconds. That means the worst timing path, worst setup path is violating by 2.99 nanoseconds. Total negative slack is 227.66. Number of violating paths are 97. We'll see what it means in much more detail in coming slides and coming lectures. So TNS, that is the total negative. So WNS is worst negative slack. TNS is the total negative slack, which is the summation of the negative slack of all the violating points. So all the 97 violating points. Okay, I think I haven't explained what is slack, so I'll explain that. It will make more sense. It tells us the area. It tells us that there are no hold constraints, which is fine. It tells us that there are no nets which have DRT violations. Let's look at if it provides any more information. So it gives us the quality of results and statistics for the current design. You can specify a significant digit. Scenario is not applicable for us. Okay, so we did a summary. Now let's look at the detailed report. The detailed report is much more bigger. So now it tells us that timing pathway. the clock name is clock. Yeah. So it tells us the clock name is clock. So we know that there's only one clock. So it tells now per clock what is the statistics. So let's say you have multiple clocks, there will be multiple entries here. It tells us that the maximum levels of logic are 12. Levels of logic means that between two registers, how many combination elements are there. Maximum there are 12. Critical path length is 3.69. That means the path delay. We look at the one of the timing reports and see what is meant by this, and then these things will become clear. So it tells us the summary of the timing. It tells us what is the cell count. So hierarchical cell count is 44. That means these are the total number of hierarchical cells. Right. It tells us what is the leaf cell count. Now leaf cell count is the total number of cells in the design. So leaf cell means a cell which is not hierarchical. So any standard cell, any memory is a hierarchical cell because there is no other cell inside it as far as design compiler is concerned. So for example, an inverter is a leaf cell because inverter is the lowest level of hierarchy that DC sees. Similarly, a memory is a leaf cell. Because why? Because we read the dotlet for the memory, and DC does not see anything inside that. It only knows the timing information and the area information for the cell. So any cell like standard cell or a memory is a leaf cell. It tells us what is the number of buffers and inverters, total number of buffers and inverters. It gives us the summary of area. It tells us what is the combination area. Non-combination area is the sum of all the sequential and memory cells. Net area is estimated from biload model. So it tells us what is the cell area. So cell area is the sum of combination and non-combinational. Design area is the sum of cell area and net area. It tells us that their total number of nets are this. There are no nets which have violations. It tells us which machine did we run. It tells us what is the resource sharing. There are some numbers on logic optimization and mapping optimization. So these are the time it takes for resource sharing, logic optimization, and mapping optimization. Overall compile time is 63 seconds, out of which these many seconds are used for resource sharing, for logic optimization. Yeah, so report QR it gives the summary of all the violations and the area. Right. Now let's look at the specific reports. Let's look at report area. Now report area again it tells. So there are many kinds of reporting commands, and some information is common to, like, for example, report area and report QR both tell us what is the area. Report area is a much more specific command. So it tells what are the libraries used, number of ports, number of nets, number of cells, number of references. Number of references means number of instances, number of nets. Then number of cells is the total number of cells in the top level, not the. We'll see how this number 12 comes. Number of ports is total amount of input and output ports. So you could, let's say I want to know how many inputs are in this design. To know the total number of inputs, we say all inputs. There's a nice command called size of collection. So I do a size of collection. This gives me the number of elements in a collection. Now since all inputs gives me a number of inputs, I can use size of collection to know the number of inputs here. So size of collection, all inputs tells me there are 34 inputs. I can do a size of collection. I guess there should be all outputs. 67 outputs. So we sum both of them. We'll have the number of ports here. They are 101, right? So there is there. So we can see how many commands like this are. So these are the commands to get the collections. So all inputs, all outputs, all registers. You can also see how many registers are there in this design. You could do this. There are 723 sequence registers here. Registers means they are all flip-flops in the design, and so on. So, but these numbers here, number of cores, number of nets, and number of cells, they refer to the current design, which is the top level design. Now I want to point out a few things in the netlist. Let's open the netlist again. So let's go to the top level design, which is the last entry. This the number of cells here is, this is one cell instruction decoder, 2, 3, 4, 5. Then we go down and see 6, 7, 8, 9, 10, 11, and 12. That is reported by the report area command. So if you want to know the total number of cells across the complete design, that means you are asking for the information of hierarchical cells. So the one reported by design compiler report area command is simply the top level. It refers to the top level design or your current design. So you could go inside, let's say you want to analyze a design which is some hierarchies down. You can change the current design to that and run a report area. We'll see one example. Let's see what design we want to. Let's say I want to know what is the instruction decoder area, separate area, right? I want to analyze now. I want to go inside and analyze how much area does each of my module take. So I can say a current design. I can change it to instruction decoder, and now I do a report area. Now it tells me that for this particular design, it uses only the standard cells. It doesn't use a memory because there's no memory inside. It tells me the number of ports, nets, cells, number of references. It tells me what is the combination area not. So you could go to any part of your design, any part of a hierarchy, and do a report area on that. So a lot of commands, most of the commands in DC work on the current design. Now I want to reset the current design to flip top. So this was all about report area. So we saw report area, report QR. Now let's look at the commands I use most, which are most effective. Report area. Then there's a command called report constraint. Let's see this. It's a very interesting thing. It again gives the summary of all the report constraints. As the name suggests, tells you it has a lot of options. It tells you what all constraints are there in your design, and if some of them get violated, how many are met. It gives all kinds of information. So what I'll do, I'll just do a report constraints without anything. So we see that all the options here are they lend specificity to this report constraint. So you want a very specific information. Let's say I want a summary of how many setup violations are there in my design. So I do a report constraint minus all violators. All violators will give just the violation. I do a setup is a max delay constraint. Strange. Okay, let me see just all violators. It says that this design has no violated constraints, and I have doubts about it. Let me do a report. Okay, let me check this design. Something has. Oh, looks like somehow the okay. Looks like when I change the current design, the constraint got overwritten. So what we'll do is we'll compile this design again, and we'll apply the clocks and input output values again. Let's see. Usually it should not happen, but looks like there's some bug with this version. I'll just Okay, let us compile the design again. So I can do just like Linux, I can search for the last command. Yeah. Now let's look at report constraints minus all violators. No, right. So somehow the constraints got erased from the design. I'm not sure why. Maybe I played with the current design, so that's why. Now what happens here is now report constraints minus all violators is a very useful command which gives you a summary of all the violations in your design. So now it tells me here that there are min, delay, hold violations. Min, delay and hold is same. We'll see why hold is called a min, delay. The clock group means that it's working on this functional clock. So all these endpoints, there is a violation of this much nature, right? Now let's see. Right now, this tells us just the pin where there is a violation. We'll see what it means by path delay and required and actual path delay by looking at the report timing command and the slack. So now let's see the most famous command of all, which is used for all kinds of timing analysis, called the report timing command. So what report timing command has a lot of options. So then I'll after explaining the report timing report, I'll go back to some of these commands. So it has probably the most extensive command there is in DC or prime time report timing. So you see, it has a lot of options. As the name suggests, report timing is used to see report a timing on a particular path, right? I'll just do a plain report timing and see what happens. Now, a plain report timing will give me, it gives me a report timing. Path type full means it will report all the cells in the path. Delay max, that means it is a setup. So there are two kinds of reports: max report and a min report. Max corresponds to a setup report, min corresponds to a hold report. Number of paths, so delay max means it's a setup kind of report. Minus max paths 1. So these are default options that it shows. Max paths means it gives me only one path. Minus, so you could want more than one path, more than, let's say you want to report the 5 worst path, you can do that. It tells me that design is the instruction decoder. So there's a problem with the current design, that is why the things are not happening. I'll have to do it again. So the current design is instruction decoder, which is not what we want. We want the chip top. So let's sorry about that. Let me change the current design to chip top again. I'll have to clear the memory. So there's a variable that contains that controls whether. So as soon as I change the design to instruction decoder to show you the area report, what design compiler did was it removed the other designs from the memory that were not used. That's why we were having all these problems. So I'll once more do stuff. I'll once more read in the design. It will take hardly a minute, and I'll set the things again. So that is why it's useful to have a report like this, have a script like this, which you can run instantaneously. I'll do a compile and try again. So at the chip top level, I was expecting to see some setup violations. I remember from the last session, but I did not see any setup violations. If you remember in the report constraints, I only saw hold violations. So now hopefully I'll see some setup violations. So what I missed applying is the load and the transition numbers. We'll do that. We'll see. So it's a blessing for us. So we'll see the usage of incremental compile. So now I'm synthesizing again with the clock in place with input delays and output delays, and I've missed applying the load and the transition. So input transition. Let's see how we can solve for that. So now there's hardly any design rule fixing. It goes down very quickly. So this is now let's look at the report timing or report. Let's look at report constraints again. Now you see, now it also tells us what is the maximum setup policy. It tells us that there is an endpoint on which there is some setup policy, right? So it gives a report, complete report, right? So what you could do is now you could go specific. You could say, show me only the setup policy. So it shows only the max delay violation. It's a big report. Now let's do a report time. So now the design here is chipped off, which is good. Operating condition, library, payload model. Now this is the start point. It tells me that start point is a rising edge progressive clock by clock. End point is an output port. Path group is clock. The path group is the clock name of the clock that captures the endpoint. Now, why do we say that clock captures the endpoint? Because we have specified the output delay on the output port with respect to clock. So this type of path is called a register to output path. Part type maps, it's a setup report. Don't worry about this. It tells us it's a payload model. This is the important point. Now please note that a setup path is a path between is a max type of path, and it starts at one clock edge, the launch clock edge, and the data is captured at the other clock edge, right? So this is the launch part. This is the launch part. So now let me also do a report clock. So the clock waveform is 0, 1, clock rises at 0, falls at 1. Clock rises at 0. Clock network delay, clock is ideal. There's no there are no delays specified on the. We have not defined any network delay. So you could define set clock latency. So if you specify a positive value, it will come here. This is 0 for a while. Now this is, it goes through the memory C pin. It goes to memory's output pin. This part, INCR part, is the delay that is consumed by a cell. So here memory consumes this delay. The path delay is nothing but the cumulative effect. So this is the list of cells that are in the path. It starts from a memory, goes through some combination logic, goes to the output port. Each of these cells, so here only output pin is listed. Each of these cells consumes, this cell consumes a 10 ps delay, this consumes a 30 ps delay, it is in nanoseconds, right? This consumes 30 ps, again 40 ps, 60 ps, 70 ps, and here there is a cumulative path. So the data arrival time at the output when the launch clock is at 0 is 3.64. Now the capture clock comes at 2. The complete total period of the clock is 2 nanoseconds. The launch edge comes at 0. For setup, the capture edge comes at 2. We have specified some clock uncertainty, which means that the capture edge can come a little bit earlier. Since it's 0.3, it gets subtracted. We have specified an output external delay. That means the data should come at least 1 nanosecond before the capture edge. Capture edge is at 2, adjusted by the uncertainty, it's 1.7. Data should come at least 1 nanosecond before capture edge, so data should arrive by 0.7, but data is arriving at 3.64. There's a problem. So the data required time is the time at which the data should be stable. Data arrival time is the actual data that arrives. If the data arrival time is less than the data required time, we say that the timing is violated. So slack is the margin we have. In this case, the margin is negative 2.94. So it's violated. Now this is a register to an output port path. If I say now let's look at the various options that are available to us. Report timing. So now after this you should be clear about what is meant by data required time, what is meant by data arrival time. Now let's look at report timing minus L. So there are so many options. Now you could go very specific. If you want the timing between two registers, you could do that by saying a report timing minus from and minus to. You could go even more specific if you want write transitions and false transitions, or you want to report a timing to a particular path. If you want the timing, if you want to increase the number of paths, for example, what I would do here now it reported only one path. So what I would do is I will ask it to tell me. I'll ask it to tell me what are the worst, let's say 5 paths. This is the worst path. The slack is minus 2.94. Now the second path starts. Start point, end point. So now it gives me 5 worst paths. Now we see that. Now see, report timing is for detailed analysis. On the other hand, report constraint was for a more summary kind of report. So I give a report. So what I'll do is, what is the good practice? What you could do, you do a report constraint minus all violators, do a minus no split, and redirect it to a violator report. I'll do a void.app. Now you go back, you open this report and see what all violations are there. Now I see here that the endpoints are all output ports. I would worry more about register to register violations than the violations at input and output ports. I'll tell you why later. Now let's focus on the register to register part, if there's any violation. Now we see here that there is some pin here that violates, and it's not a port. However, it might have a violation starting from input port. This is just the endpoint. The leftmost column is the endpoint. So, and don't worry about the whole violation for now. Let me see if all these pins are reset pins. So they must be similar kind of paths. Let's see what is this violation. Go back. Now I want a specific report. So I go back to report timing. I say report timing minus 2, and I check out this one. So now see, the start point is a register and the end point is also a register. So this is a register to register path. It tells us what is the Y-load model used for different designs, since it's the automatic area based Y-load model. Clock writes is a launch part. Launch for a register to register path will happen at the clock edge. If you go back and see the lecture slide, it starts at the clock edge. It goes from clock to queue. Clock. It goes through all these combination logic. So there is a big combination logic. It goes to the multipliers register pin. There's some top register pin. Now here, so there's the launch clock arrives at 2. Sorry, the capture clock arrives at 2, as in the register for uncertainty. Now, when we saw the register to output path, we subtracted the output delay. In this case, the output delay is replaced by the library setup time. Library setup time tells us that the data should come this much time earlier than the capture edge. It is a setup time constraint. So it is subtracted again. So data required time is 1.57, data arrival time is 2.92. Slack again is violated. Now what does this tell us? At the first glance, this tells us that our design is not suitable to work at 500 megahertz. Why? Because for a violation of, for a clock period of 2 nanoseconds, our design violates by this much amount. So I'll do some calculation. My period was 2.2 ms. The violation is 1.36 for register to register path. So if my period was 3.36 nanoseconds, then this might have met. So this is a straightforward calculation. Now I calculate the frequency, and at 297 megahertz, without even going for recompilation, I can say that my design will work. This is how we estimate the performance of a design. And now we know that this design will not work at 500 megahertz. Now there can be multiple reasons. First reason could be that you are aiming for a much higher frequency, but your design is not good. Second indication could be that your design is good, you are confident on a design, but it is not supported by your standard cell library. Now in this case, for example, you synthesize a design in 65 nanometer, but you find, oh boss, I am not using my design, my planning question. So what you could do, either improve the design or decide whether you want to go to a lower technology. Because if you go from 65 nanometer to 45 nanometer, your standard cells will become faster. So this performance is truly limited by both the design. Now here one thing I see that there are so many combination elements in this critical path. So this is the critical path. Critical path means this is the violation, worst case violation on register to register path. I see there are so many levels of logic here. I see there are like about maybe 20 odd, and when there are 20 levels of logic, 500 megahertz is a very high frequency, right, to aim for. Now somebody might ask that let's open the violation report again. Now somebody might ask that there is more violation on the output port, so why aren't we worried about it? Now let's see. So what I'll do is this is the way you could report the worst path ending at the output port. Now it's the same report as before. Now I see that there is one more factor here, which is output exponential. In the register to register case, it was the library setup time. Now the library setup time is something that is fixed. We cannot play with it. But output external delay is something we can play with. How? Now I am assigning 1 nanosecond to the external world. My period is 2 nanoseconds. I am assigning 50% of the time to the external world. This is one problem. I could play with this. If I know that the part of the script that is capturing this output code does not need 1 nanosecond, so I can take some time away from it. I can reduce my output delay, so that will reduce the violation. Second problem I see is that the path starts at memory. Memory itself is taking 2.9 nanoseconds. So I can never work faster than this. So my memory is slow. Right? Third thing is that if the memory is slow, then I should not have a path from the memory to output port. I should have a clock here. I should have some kind of pipelining here. So there's one guideline that is violated here, which is that I should register my input and output. If this output was registered, that means so usually for slower memory you should have a pipeline clock. That means there should be a clock right after this. So what I would recommend to you is that you go back and understand the design a bit, the example design, and see if you can improve it. Third thing I see is that these drivers this is an X0 driver. This is a very slow driver. So maybe I could upsize it. How I can upsize it? Now, so why is DC using a low driver here? Why isn't it upsizing it? DC knows that it has a big violation, and we did not have any design rule constraint. We did not apply any restrictive design rule constraint apart from what is in the library. So it did not optimize this path well. So it happens a lot of times when there are violations, when there is a clash between different groups. And DC will optimize one group of paths at the cost of others. Now going back to the constraints, I said that I forgot to apply the I forgot to apply the input function and output load. Now what do? I can do it again. I'll apply set input condition. Let me apply a 0.5 at from selection all inputs. I apply the load. Now, do I need to do a full compile again? No. Now I could do is I did this compile. Now I'll just add an incremental. So I updated a constraint. I updated the design rule constraint. It is not a very major thing. So I can choose to do an incremental synthesis, which will be comparatively faster than a full synthesis. Right? So now it will do design rule fixing, and it will spend a bit more time on it. So if there are some violations. So in case you did an incremental synthesis and find that it is not improving a lot, I would recommend start from scratch again, because starting from scratch, so see, there are design rule violations here. Are there? No, design rule cost is 0. So design rule is not fixed. Now let's see the timing again. So now you notice that the inverter that drives the output is now upsized. Where do we have the report of this? So this is now an X8 inverter. Why an X8 inverter? Because we specified a load, an increased load. Now forget about the timing problems in the design. I'll just show you the power of report timing. So what all we could do. Now I'll speak some typical scenarios. I'll talk about some typical scenarios and how to report timing on that. I want to see the worst case timing starting from an input port. Report timing minus from all inputs. Now this command will report timing starting from all inputs and going anywhere, either to a register or to an output port, but it will show only the worst case path. This is the worst case path. It starts at an input that we specified. It goes to an endpoint, which is a register, so it's an input to register path. And we saw what this means, right? There is some small violation here. Now I want to see 5 worst paths starting from inputs. Simply do a max paths. It will tell me all the paths. Now I want to see. Let's say I want to see the worst case register to register path. Now this is a bit tricky. So what I could do is, now here in this case there is no separate group of inputs and outputs. All the path group here is a very powerful thing to have. Path group is always determined by the capture clock. In case of input to register path, since the registers, all registers are at the same clock, it's always the clock group is clock. All the register to register path have the group clock. All the register to output paths, since the output ports are captured by again the same clock, so for all the clock group is same, which is the group clock. So I can do something like a group path. I can say group path. I'll maybe deal with this a bit later. So let's see what group path means first. So this group path serves 2 purposes. It will tell you how to. It gives you the power to create a new clock group, new path group, and in turn you could also control the optimization on this group path. Whenever you create a group, by default you tell DC that I am creating this group because I want you to pay more attention on this. So you could do this for critical paths also. This comes under advanced synthesis technique, but you could do this to create separate groups, right? And you could use those path groups to report timing. There's one more way to report timing on register to register path is by doing this minus from all registers -2 all registers. So it gives some warnings. Okay, it complains that you should have. What I'll do is I would need some. Let me try one more example. Second thing, what you could do is I'll have to write a procedure for it. That's why the group path is more sophisticated. Plus the command report timing in DC is a subset of the report timing command in prime time, which is much more powerful. So when we come to prime time, we see that a lot of things work better there. The prime time design timing. So the prime time timing engine means the software that will do all the delay calculation and will show you the report timing report. The prime time timing engine is much more superior to design compiler. Design compiler commands for timing are very basic versions of that. So a lot of things we'll see will start working in prime time that are not working here. So I have to write a procedure to report register to register path. That is why it's very useful to create groups from the starting. We'll see that in the next lab perhaps. Now we saw how to report the worst path. We saw how to report form and 2. Apart from timing, report timing also tells what are the load and transition numbers. So we could do this, and let's say we just do this, so it will show us the worst path. Again, it's the same path, but now it will start telling us what is the capacitance. So here, this is the capacitance, this is the transition. So if you see, what I'll do is also expand a bit and say it only shows the input pins here. I'll also show the only shows the output pins here. The Y is the output of each cell. We also want to see what is the input pin, and let's say we also want to see the net. So now the report is much more extensive. So now there's it starts with a clock. So there's a clock here at C1 clock. We set the clock. If you remember, we set the clock transition number to be 0.5. It is coming here. This is the net which has this cap. This net cap might be coming from the Y load model. So now C1 to data out. This is the net now again. So now you see multiple levels. So for let's say for NAND cell, we see that what is the net that drives it, what is the fan out of this net, what is the capacitance at this net. We see so let's see this inverter. At the input A, this is the transition. This is the delay part incremental. This is the cumulative delay part. This inverter input pin is driven by this net, which in turn comes from this memory. Right. Similarly, you could do it for any cell. Let's look at this AND cell. So input is A1, output is Y. This is the net which has a fan out of 2. This is the capacitance. These are the transition. So the transition numbers are reported for both input and output pin. The capacitance is only reported at the net, which makes sense. So now, for example, this total cap, this 0.87, might be is it the sum of the net cap itself, the net N2 itself, plus the capacitance output cap at Y. It's the sum of both, right? And so this is the net capacitances are based on the Y load model. So this is the way you could report more extensive data using the report timing command. So now I'll request you to experiment with report timing command. There are so many options available here to work with. Minus significant digits is one. You could read more about it by doing the man page, and you could try at least these options: minus from, minus to, minus through. There's also an option called minus path type. So there's an option called minus path. We could say end, and it will tell us only the endpoint. So this is very similar to the report constraint report. In this case, it will give since we gave n, it will give all the endpoints that are violated. Right? So this is very similar to the report constraint report. Plus, it is not giving us violations now. It is also giving us the path those are meeting. Right? Right. So now when we apply constraints, we want to check few things. So there's a command called check timing. So when I run check timing, DC is telling, it is checking few things and it is telling if there are any problems. It is checking generated clocks. There are no generated clocks. We'll talk about generated clocks when we come to unit 5. It is checking combination loops. It is checking input delay. So it is checking so many things. If there is something absent, if there is some problem, then DC will tell here. This design apparently right now doesn't have any problem like this. Again, check timing is much more powerful in prime time, and we'll see a lot more of that in prime time. So the aim of design compiler is to do a performance and area analysis. Performance and area analysis requires you to set clock frequency, set area goals, and you are done for most of the cases. We saw the report timing on when we do a report timing, it gives us only the setup path, right? How to report the hold path? We do a delay min. This will tell you what is the hold path. Now see the difference here. It tells us delay min. Now this is the timing is coming from register to register. Path type is min, which means it's a hold path. Now here, this is the launch path. Clock comes at 0. This is the clock to queue timing, and that's it. It goes to the memories pin, some pin, I121 pin. Now the capture is also at the same clock as 0. So the hold path, if you go back to the figure and see, the hold path is checked on the same clock edge. The launch and capture edges are same. There is no concept of frequency here. Hold is frequency independent. For max path, for setup paths, it will pick up the path with the maximum delay, and the path with the maximum delay is bound to have lot of levels of logic. For hold path, it will pick up the fastest path. That is why it is also called the min path. Now for hold, this is the launch part. There is just a flop. There is no combination logic there. The capture edge is the same. There is a clock uncertainty. Now it will get added. That means the capture edge will come later. So capture at 0, adjusted for clock uncertainty 0.3. The library hold time for this pin, the library hold time is 0.2. So this is the clock path. The library hold time is 0.2. So the data required time is 0.5. That means if the clock edge is coming at 0, the data should be stable till 0.5. But the data is getting altered at 0.22. Till 0.5 the old data should have remained, but the new data is coming at 0.22. The violation is 0.5 minus 0.22, 0.28, sorry. And this does not depend on the clock frequency. There is no clock frequency in picture here, right? You'll see a lot more of this in unit 5. Please note that for hold timing, you should not be concerned about the hold timing in synthesis reports. In most of the cases, there are very special cases where you should worry about the hold timing. But as a thumb rule, after synthesis, check the area, check the report constraints minus all violators, and if you see violations, analyze the setup paths. Forget about the hold paths for now. I summarize the report timing report again. This is the clock launch. This is the data path. So this is the clock pin. It will go first to the clock pin. This is the data path. So the first half of the report is the data path, which at the end of it you will come up with the data arrival time. The second part of the report is the capture path, which is the clock capture path. There will be adjustments for clock uncertainty, library setup time, or output external delay, or something like that. At the end of which you will come up with the data required time. The difference between data required time and data arrival time is the slack. If the slack is less than 0, it will show as violated. If the slack is greater than 0, it will tell us met. Right? This is the way you interpret the report timing report. It is one of the most important things you should learn for doing a good synthesis and for doing a good timing analysis. Right. So in the next in the unit 5 you would see more on this. Probably I'll have one more lab on this with some advanced synthesis techniques and some advanced usage of report timing. That will be a bit of an advanced lab. So it will be very good to get your hands get hands-on experience in the first 3 labs. Also, please go and analyze the design yourself. See what all design guidelines are not followed. For example, if the inputs are registered, if the outputs are registered, and so on. Analyze that problem, correct it, and using the same library, we saw that the timing needs at about 300 megahertz. Maybe you should try and make this design work at 350 or 400 megahertz by doing some design changes if you can. So that's a significant assignment for you to follow. So we will see more advanced features of design compiler, of compile command and group paths and so on in the next session. Thank you.